Hello, class. We're going to learn about circular motion and gravitation. Circular motion is any object moving along a circular path. For now, we're going to assume the velocity of the object moving along a circular path is constant, meaning the velocity does not change. The direction of velocity at an instant is tangent to the circular path. This is observed below in the figure below as V1 and V2. In this course, I'm not going to derive the following equation. You're just going to have to trust me that the radial acceleration, or also known as centripetal acceleration, always points towards the center of the circle, and the equation for radial acceleration is equal to v squared over r. V stands for constant velocity of the object that is traveling around the circular path, and r stands for the radius of the circle that the object is traveling around. Here is a figure showing the direction for the centripetal acceleration and velocity of the object moving along the circular path. For our first example, we have a 150-gram ball at the end of a string that is revolving uniformly in a horizontal circle with a radius of 0.6 meters. The ball makes a 2 revolution in a second. What is the centripetal acceleration? Well, let's apply our new equation for centripetal acceleration. However, we don't know the value for speed, but we can calculate speed by using the basic definition of distance over time. The distance around a circle equals the value of the circumference, which is 2 pi r, and the time equals how long it takes to complete one revolution around the circle, which is also the definition of a period, capital T. Plug and chug, and we get 7.54 meters per second. And now we can plug and chug to solve for centripetal acceleration, which is 94.7 meters per second. Now, let's bring back your favorite equation, Newton's second law, which states that sum of the forces equals mass times acceleration. When you're dealing with an object moving in a circular path, you follow the same steps and process for solving unknowns in Newton's equation as before with drawing a free body diagram. The only major difference is to replace the acceleration with centripetal acceleration or radial acceleration, where you may need to use a definition of radial acceleration of v squared over r. One thing I really want to emphasize is in order for an object to travel in a circular path, there must be a force to cause the object to move in a circular path. That force comes in many forms, such as tension, which can be created by tying an object on a rope and swinging this object around in circles, as shown in the figure below. In this example, we want to estimate the force that a person must exert on a string attached to a 0.15 kilogram ball to make the ball revolve in a horizontal circle with a radius of 0.6 meter. The ball makes 2 revolutions per second, so the period is a half a second. Just like any force problem, we apply sum of the forces equals ma. However, since we're dealing with an object that's moving in a circular motion, I will write sub to r to represent the radial direction instead of x or y. For the radial direction, any vectors pointing inward will be positive, and the force vectors pointing outward will be negative. Also notice that I wrote the sub to c, which stands for centripetal acceleration. In this video, I will continue using AC instead of AR. An object moving in a circular motion will always have centripetal acceleration pointing inward radially. The only force acting on the object in this example that we have pointing radially inward is tension. Since tension is pointing inward, the value is positive. We can consider tension our centripetal force because it's this force that causes the ball to move in a circular motion. Next, we plug in the equation for centripetal acceleration, which is v squared over r. However, we don't know the value of speed again. But, just like our previous problem, the distance around the circle is 2 pi r, and the time equals the period to complete one revolution. Plug and chug, and we get 7.54 meters per second. And now we can plug and chug to obtain tension, which equals 14 newtons. Next example. We have a 0.15 kilogram ball on the end of a 1.1 meter long cord which is swung in a vertical circle. For part A, we want to determine the minimum speed that the ball must have at the top of its arc so that the ball continues to move in a circle. Again, for any object moving in a circular motion, we have sum of the forces in the radial direction equals MAC. At the top of the path, we have two force vectors pointing inward, so their values are positive. And we are also plugging in the equation for centripetal acceleration. Now, the trick with determining the minimum speed is that the force causing the ball to move in a circular motion equals 0 at the top. That will give you the most extreme condition for the minimum speed required to make it around. In this example, tension is our centripetal force, and therefore we would set tension equal to 0. Now we're left with a more simplified equation. And look what else cancels out. Mass. Now our equation really simplifies. Rearrange to solve for the minimum speed required, which is the square root of g. Plug and chug, and we get 3.28 meters per second. For part B, we'll need this value as we assume the minimum speed at the bottom is twice the speed at the top. So we get 6.57 meters per second for the speed at the bottom. Again, we'll start with sum of the forces in the radial direction equals MAC. For our forces, we have tension pointing inward and weight pointing downward, or outward. So it's negative. And again, make a substitution for centripetal acceleration. Rearrange the equation to solve for tension. Factor out mass. Plug and chug, and we get 7.34 or 35 newtons. Now, for regular physics, we'll discuss the car moving around an unbanked car, or unbanked. For those wishing to take an AP course, please look at the example in your textbook for solving a car going around a banked turn. In this example, we have a 1,000 kilogram car that rounds a curve on a flat road of radius 50 meters at a speed of 15 meters per second. Will the car follow the curve or will it skid? Now assume that the pavement is dry and the coefficient of static friction is 0.6. And then for part B, we'll assume it's icy and now the static coefficient is 0.25. In this example, the first step is to draw your free body diagram. For the top view, we have friction pointing inward. Friction is a centripetal force and the reason why the car is moving in a circular path. If the road were icy, the car would not turn. The left figure shows the free body diagram with the y direction included. This will be important since friction equals mu times the normal force. In this example, since we're concerned about the car not sliding and relying on static friction, we need to find the maximum static friction to compare with if our car will slide or not. But first, we need to do some of the forces in the y direction to eventually solve for the normal force value. The y direction equals 0 because the car is not flying and it's not sinking in the ground. We write down all our force vectors in the y direction. Solve for the normal force. Plug and chug, and we get 98,000 newtons. Now we can plug and chug to solve for the maximum static friction, which is 5,880 newtons. So let's see if our friction pointing radially inward will be less than 5,880 newtons. If so, our car will not slide. We start with sum of the forces in the radial direction equals MAC. Our only force radially is friction pointing inward. Substitute the equation for centripetal acceleration. Plug and chug, and we get 4,500 newtons. Will our car slide? No, because the value is less than the maximum breaking point for static friction. Now, for part B, our road is icy, so our maximum breaking point for static friction will change. Let's make the substitution in for our new coefficient of static friction of 0.25 with the same value of normal force. Will our car slide now? Yes, because 4,500 is greater than our breaking point in static friction, so our car will slide. Whoops, there we go. So the maximum friction is 2450 newtons, so therefore our car will slide. We just saw that friction is a good example of force used to set an object in a circular path, because the car uses friction of the road to make turns. If the road was made out of ice, creating a friction of near zero, there is no force acting on the car to help it turn in a circular path. Now, the last note about circular motion is that if you cut a string of an object spinning in circles, the object will continue in a path at that instant, which is the bottom figure, because you just removed the inward force causing it to move in a circular path. Notice that there is no outward force as shown in the figure above.